Okay. Okay, so today I am going to solve this problem here. It's called searching rotated sorted array. And it's a medium difficulty problem. Let me see. I'm not sure if I'm sharing this screen here yet. Okay. Sorry about that. Screen two, perfect. Okay. Yeah, so basically, this problem is medium difficulty and is asked a lot by Amazon and Facebook, Google. Amazon has asked it a lot in the last 6 months. Okay, so one thing to note here is that the solution for this problem entails a binary search, and also binary search is actually very useful, or well, can only be implemented if the array is sorted. But then there is also like a small detail, because the array actually will be, it says it's rotated. Now we're going to see what that means after reading the problem statement, which is the following. There is an integer array nums sorted in ascending order with distinct values. Prior to being passed to your function, nums is possibly rotated at an unknown pivot index, such that the resulting array is num k plus 1, nums n minus 1, and num 0, nums 1, etc., all the way to nums k minus 1. For example, this array 0, 1, 2, 4, 5, 6, 7 might be rotated at pivot index 3 and become 4, 5, 6, 7, 0, 1, and 2. So yeah, so we can see that basically this will convert the array into like non-sorted, right? And then after that, we have to search the target inside the array, and if it does not exist, we have to return -1. And then our algorithm must be have a runtime complexity of log of n. So I mean, of course, this problem will be extremely trivial if we didn't have this constraint. But also, like, if we see these constraints here, I'm not sure if a brute force approach will still pass if we have this size of input, but I don't think so, because we can be between 5,000 elements or 1. So for example, here are examples. We have this array, and then our target is 0. 0 does exist, and is at index 4. So 0, 1, 2, 3, 4. And then 3 doesn't exist in this array, so it returns -1. 0 doesn't exist here, so it returns -1. Okay, cool. So let's go here to the board, and I'm gonna copy this text here. And I'm gonna spread this out. Okay, so since our input array will most likely always be sorted, I mean, we still have to handle that condition. We basically need to identify first, like a portion of the array, because we know like there's a portion here, like if we draw like an imaginary line, we know that this part of the array is sorted in ascending order, right? 4, 5, 6, 7. And then this part of the array is also sorted in ascending order, right? So for example, we could have this is our left part, and this is our right part. So in order to solve this problem and apply, like, let's say, the binary search, we will need to decide in what part of the input are we gonna basically do the binary search. So for this, we will need to find basically the minimum element of the array, or basically the breaking point, right? The pivot index. So in this case, it will be always the smallest value in the array. So the way this is going to be done is that we will also do binary search, but it's going to be in a different way to do that first first approach. So first thing we need to do is find min element. And then the other thing we need to do after that is determine where to search, left or right. And then the last thing we need to do is apply binary in left or right. Okay. So it's basically the steps at a high level. So, okay, so to find the minimum element, this first, or index actually, the index of min element. And let me put this smaller. The index of the minimum element. So I'm gonna draw here really quick the indexes as well. So we have 0, 1, 2, 3, 4, 5, and 6. We'll have here our binary search also has a start and end pointer here. So the way we're gonna do that is basically we're gonna compute always like our middle index. So we'll have a middle index, and that is basically going to equal our start pointer plus our end pointer divided by 2. So for example, in the first iteration, we will have 6 divided by 2, and then that will be equal to 3, right? So then our middle pointer will be equal to 3 here. And then after that, we're gonna check, we are always going to check if the value at that middle pointer index, so in this case is smaller or larger than the value at the last element of the array. Okay, let me put here red as well, at the last element of the array here. And basically, if it is small, if it is smaller, we know that we need to basically search to the right, sorry, to the left. And if it's larger, we know that we need to search towards the right. And then that's how, well, I'm not really explaining in detail here how binary search works. But basically binary search reduces the input by half on each iteration by either like exploring the left side or the right side, and then dividing those sides by half, basically until we find what we're trying to search. But then that's why that algorithm is basically log of n time complexity, because the input size reduces by half each iteration. So instead of being incrementing, it's being reduced by half. And then of course, a logarithm is the inverse operation of an exponential operation. So that's why it will run much quicker, because the search space is being reduced every time. Okay, so for example here, like 7 will be larger than 2. So in that case, we will move. So let me just go here again. So 7 is larger than 2. So in this case, what we have to do is that we will move the start pointer. So from here, we're gonna move it. It's gonna be moved to here. And then this is our endpoint. So then now we're gonna be looking at this part of the array, right? So if I'm gonna just write that out, our start pointer will equal the middle index plus 1, right? So our middle index was 3, and then plus 1 is 4. So that's why the start pointer will move here. Of course, We will only do that if nums and middle index is larger than nums last index, right? N minus 1. And then we will apply this operation again. So then let's say our search space is now here. We still have the same indexes. So I'm just going to write them here. So we have 4, 5, and 6. And then we do the same operation. We do the same operation. So this will be 4 plus 6 is 10. Divided by 2 is 5. So then we have here 5, and then 1. 1 is smaller than 2, right? 1 is smaller than this. So then we know that the smallest value should be to the left of this, of the middle index. So should be this, right? So what that means, if I draw here my start pointer and the end pointer. So the end pointer is basically going to be, sorry. The end pointer will then move here as well, right? And then our end pointer will be here eventually. So why is that? Because we have here our end pointer. Our end pointer will be the middle, this middle index minus 1 if this number is smaller than the last element in the array. So basically, this is kind of like also like a greedy approach, right? So if it's smaller, like we reduce it towards the left, right? So we move the end pointer towards the left. And here, if it's actually larger, if this number is larger, we move the start point towards the end, because we're assuming like, okay, actually the smallest value should be more to the right of the search space. So that is how we are going to find that index. And then of course, at the end, after this, we will basically have only one number, right? Which is 0, which our start and end pointer will be at. And basically we will return this index here, right? So this will basically be, if I do this will basically be 4 plus 4 is 8, right? Because 0 is at index 4. So 8 divided by 2 is 4. So we would return the index, right? So find index of min element. So that is how this should work. So let's write that really quick. Let me send here erase it by mistake. So if I have here my method, so private int, so find, let's call it find min and then we have here our nums, and we're gonna have n as well, int n. And by the way, I'm also using the C# because I haven't basically used it in a very long time. I actually really like this language, so I want to just get the feeling of it again. So that's why I'm not using Python right now. Okay, so let's start to implement that. So we will have our end pointer. We will have it at the last n minus 1, and then we are going to have our start pointer going to be at 0. Going to be at 0, and then we're going to basically loop. So, well, start pointer is smaller than or equal to end pointer. We're going to loop through this, so we're going to have our middle. So we're gonna have our middle index. So we're gonna have start plus end pointer divided by 2. And also when C#, when we add two integers, well, when we divide an integer with another integer, and if the result is a decimal, so for example, like if this is 2.6, they will return it will round it to the value closer to 0. So it will return 2. This is how basically it works. It will do it by default. In Python, we will have to like add something like this, like double for division. Okay, so now we have if the value that is pointed to, right? So we have nums, and then we have middle index. So if the value that's pointed to the middle index is smaller than or equal to the value at the end, so we have nums n minus 1, we know that we have to move the end pointer inwards, right? So end pointer equals middle index minus 1. But actually, no, let's just do that. So we do it how we were explaining it actually, sorry. So we're gonna do this one. So 7, right? So is 7 larger? Then we're gonna move the start pointer, right? So we're gonna move our start pointer upwards, right? Because then we know smallest one has to be closer to or towards the endpoint. And then we are going to have here like our target index. And this should be, yeah, let's just have it here. Okay, and then we are going to say target index equals middle index. And if, so now we have else, if it's the other way around, well, we're gonna say end pointer, we're gonna move it inwards, right? So if nums is smaller, if this thing is smaller, if whatever is pointing to, if whatever the middle index is pointed to is smaller than the last element, then we know that we should move to the left of the array, right? So then we move the end pointer towards the left. So for example, here in this scenario, right? So 1 is smaller than 2. So we move the end pointer to the left of the middle index. So it'll be 0. So this will handle this situation. And then at the end, we will return our target index. So that is the idea of this. So let's test. Let's test this. So we have our int n equals nums dot length, and then we have here console dot right line, and we have here this dot find element at mean index. So we have it nums and n. And then let's have this called in pivot index. And let's see what's happening here. So let me just erase these guys and let me do some other tests here, like for example, 2 and 5. And let's say the target is 2 or something. But then this should return 0, right, for the pivot index. And then this one should return 4. I believe we also need to return, otherwise it will complain. So return -1. Okay, so let's see pivot index. Let's see what it will do. Forgot semicolons, of course. So let's return. Does not contain a definition for length. Why doesn't it contain? Should probably is because it's upper. Okay, so pivot index, it's 3, correct? And here, pivot index is -1. Okay, I think I made a small mistake here. So actually, if it's smaller than or equal, yeah, we will do this, but then we have to modify the end index, so endpoint, sorry. Endpoint here, and this has to be negative. And then our start point should be, we increment it here. Let's run it again. So we have pivot index 4, 0, 1, 2, 3, 4. And pivot index 0, perfect. So 0. Yeah. So yeah, I just made a mistake here on the signs here. Okay. Okay, cool. Yeah, makes sense. So perfect. So now we can. So we know that this is working. I mean, yeah, it should be working here. So now after this, we need to determine how we are going to, if we're gonna search to the left or to the right. So we can say determine. So we're gonna do in this second step, right? Determine where to search. So we're gonna do this, determine where to search, left or right. So the way we're gonna do that is if we're gonna say the last element, if the last element is smaller than our target, so we know that our endpoint, so our end pointer will be pivot index here, are set to the pivot index. We also need to have these guys here, except this is also gonna be now 0. So if our last element is smaller than the target, we basically know that we have to search to the left, right? So search left. And let's see if so we have the opposite condition. So if the last element is larger than the target, we know that we need to search right. So start point, this will be pivot, right? And our end pointer, I have to actually remove this integer. Our end pointer will be n-1, so we'll be pointing at the last index. Okay, otherwise, basically means like if these things are equal, we return the index of the last element, right? n-1. n-1. So let's just grab this guy here for a second. And I'm gonna put it here for reference. So let's say here this returns the pivot index will be 4, right? And pivot index will be 4. But we have the target. So the target is 0, and 0 is already smaller than the last element, right? 0 is smaller than the last element. So that's why we're gonna basically search left. So we're gonna place the end pointer and we're to the pivot index, right? Which is 4. So we're gonna search like this, including the pivot index. But let's say the array, we have to search for 1. So 1 is larger than the, sorry. So 2 is still 2 is larger than the target. Sorry, 1 will still be, 1 is a target. And so this will still, so yeah, well, it's kind of confused myself actually when when searching, when changing this the search target. So let's say if the search target, I'm just gonna write it here. So let's say T is 1. If T is 1, and then this one here, so 2 is not smaller than the target, right? So 2 is larger than the target. So in this case, of course, we will search to the right, right? So the start pointer will move here. So then we will search from this area, including the pivot index 0, 1, and 2. And of course, the end pointer will be here. So we were search right. Otherwise, we return this, right? We return this. Okay. So now let's do binary search. So apply binary search, right? Like the traditional binary search. So we can recycle some of this stuff. So let's recycle. And then we have our middle index. And basically we can say if nums middle index is smaller than target, oops, smaller than target, and then of course we have this here. So we know the middle index in this case it will be here, right? So then this will be 4, 5, and 6. So 4 plus so then this will be 5, right? So 1 is smaller than the target because the target, for example, here is this will be false in this case. So this will be false. So in this case, else if we have this condition here, right, which is the one we're going to do, will be the opposite. So we have, so 1 is larger than the target. So we know we now need to look left, right? Search left, and what that means is that we're gonna grab this guy. So search left means endpoint, or sorry, yeah, and endpoint is gonna equals middle index minus 1, and then this one is gonna be, of course, start index, or our start pointer is gonna be moved here, right? We can say search left. So that's gonna be it. And then we know that if this equals the target, we will obviously return the index, okay? So curly, or this semicolon stuff I'm missing here, right? So let's say, okay, so here we have 0, we have 5, so 1 is one is larger than the target. So then we will move the end pointer, which is here to here, right? Which it will be the same as the start pointer. So then after that, of course, this will be all false. It will be equal, so we return the middle index. So this should work. So let's run this and test. Okay. Semicolon missing. So these are working. So now let's also reset. I'm gonna reset the test cases. So let's reset here. This is also, everything is working here as expected. Okay, let's submit the results and see. Okay, cool. So it did work. So let's resubmit. Okay, nice. Cool. So yeah, this is the logic of this solution. So yeah, I just think the interesting thing about this is how like binary search can also be applied when we're not like specifically looking for like a target, but we're like trying to reduce the search space with a binary condition. Like for example, here we're gonna reduce it left to right until we basically satisfy a condition. And then of course here we can use the traditional template to search for a value. So yeah, so for example here, this the array wasn't sorted in this case, right? Because it was rotated, but we could still apply binary search because we were searching for the minimum element in that array. So this is an interesting thing to take into account. And in terms of time complexity, so the time complexity, well, let me maybe do it here perhaps, so it's more clear. So say time complexity. So what that is we have the big O of log of n. So we have log of n plus log of n. And why we have log of n plus log of n? Because we have two binary searches. We have this one, and we have this one, right? So, and then of course, this could be simplified to big O of n and 2 times log of n. And then this could, of course, be further simplified to big O of n log of n. Because in big O, we just drop the constant factor, so it becomes log of n. And in terms of space complexity, it will be constant. It will be constant. Because we're not like storing any additional values, and like storing values in variables is always takes a constant space complexity. So yeah, so this is basically the analysis of the solution.